somewhere in our galaxy, at some time in the future, a spacecraft from Earth will encounter the most dangerous object in the universe.
This is an object that is not made from ordinary matter. It's not made from antimatter. It isn't made of matter at all. It's made out of a pure warpage of space and time.
Nothing comes out of it. Things only go into it. It's that one-way nature which probably upsets people most, causes them to be really disturbed, and in fact causes many scientists to be disturbed.
That's why it was quite surprising when astronomers found that there was really good reason to suspect that the universe should be full of these extraordinary objects.
At some time in the future, a spacecraft from Earth will encounter an extraordinary universe full of black holes. Everybody has heard of black holes. No one has really seen them. The spacecraft of our dreams has reached not a solid object, but the boundary to a region of space where gravity has gone mad. Waiting below is a black hole in space. This is where a mighty star has died and left a bottomless pit from which there is no escape. Welcome to the edge of the universe and to the end of space and time. Phil Charles not only dreams black holes, he hunts them down for a living. He's found the strongest evidence yet for a black hole lurking in our own galactic backyard.
Searching for these things is the most wonderful way of going to the frontiers of modern physics. The most exciting thing that the modern scientists can do. Pulled up the spectra using figure eight, and that was fine.
By day, Phil Charles lectures on astrophysical theory at Oxford University.
Only visible from the southern hemisphere.
By night, he is at the forefront of the hunt for astrophysical facts.
To be a successful black hole hunter, you have to have ready access to the largest ground-based telescopes. We have to go all over the world to La Palma and Hawaii in the northern hemisphere, to South Africa, Chile, and Australia in the southern hemisphere.
Around the globe, Phil Charles and his fellow astronomers call upon the world's most sophisticated astronomical arsenal to probe the depths of space for these mystery objects. From X-ray satellites and the Hubble Space Telescope in orbit, to the finest radio and optical telescopes on the ground. Today's destination is La Palma in the Canary Islands.
La Palma is definitely one of my favorite places. I've been studying black holes on La Palma for over 7 years now.
The very nature of black holes makes them elusive quarry. By definition, they can't be seen.
If you imagine you have a black hole and material is falling into it.
Only in the 1990s has mainstream science come to a consensus that black holes might actually exist.
Gravitational collapse.
Theory tells us that deep inside black holes, everything we know about the universe will come to an end.
I was concerned about whether this would ever have any relevance to the real universe.
But the mathematics is unequivocal. When a massive star dies, it will have no choice but to form a black hole. For astronomers like Phil Charles, black holes remain the big game of the universe. But how do you catch a small, invisible nothing that may be hundreds or thousands of light years away across the noisy ocean of space? With more stars in the heavens than all the grains of sand on all the world's beaches, how do you hunt for that one dark star that swallows light rather than shines like a beacon? Astronomers must hunt not for black holes themselves, but for the effects they generate in space around them. Phil Charles looks for visible stars that black holes might have trapped in orbit. But even they can be hard to find.
When you are looking for a needle in a haystack, we need the needle to shout out and say we're here. That we do through the fact that in the late 1980s, the Japanese launched an X-ray satellite called Ginga, which had what we call an all-sky monitor on it for detecting X-rays from anywhere in the sky. It's the X-rays that alert us to the presence of this needle, the needle in the haystack that we're searching for.
While sweeping the heavens in 1989, the Ginga satellite reported a mysterious burst of X-rays in our own galactic neighborhood. The source of the radiation was an invisible object 3,000 light-years away, around which a faint star seemed to be circling. The star had the catalogue name V404 Cygni. It was just the star Phil Charles had been looking for. Phil Charles' prime weapon in the search for black holes is the massive William Herschel telescope, perched on the rim of an extinct volcano 2.5 kilometers above the Atlantic Ocean.
Okay, Renee, the grating's loaded, so we're all set to go. It's V404.
For the last 7 years, Charles has pointed the telescope towards the star V404, trying to work out just what sort of highly compact object the star must be circling.
Okay, let's start the integration.
Yeah, it's looking good.
The most likely candidate is a stellar mass black hole, the most common kind. According to the theory, such a black hole should weigh 10 times as much as a star like our Sun, but would only be about the diameter of central London. Less common is a second type of black hole, supermassive heavyweights believed to lurk in the heart of galaxies. But to understand any black hole, you must begin with gravity, for within this darkness, gravity is in total control. Our modern quest to understand gravity and ultimately black holes was born in this room on Christmas Day 1642. But it was a shaky start. The great Isaac Newton was premature and only just survived his first day of life. Showing little promise as a farmer, the young Isaac Newton was sent up to Cambridge University. As an academic, Newton would formulate laws of physics which still form the basis of modern science. Fate played its part. In 1665, the plague swept across England. Cambridge was closed to help contain the spread of the contagion. Newton was forced to flee. He sought refuge back at Woolsthorpe Manor. Over the next 18 months here, he was to discover the mathematics of calculus, to formulate laws for the motion of the planets, and to unravel the spectral nature of light. And one day, a falling apple interrupted his thoughts and led him to ponder gravity itself.
Newton was the first person to give us a really detailed mathematical understanding of one of the basic forces of nature. And, of course, it was the first great triumph of mathematical physics. He told us that the force which holds us down here on the Earth and which allows an apple to fall is the same force which holds the moon in its orbit around the Earth and makes the planets move in their courses.
Newton reasoned that all matter in the universe has gravity, that it's a force that reaches out from one body to another and pulls everything inwards. The more mass an object has, the more gravity, the stronger this inward pull. The first person to combine this notion of the inward pull of gravity with knowledge that the speed of light was finite was John Michell. As rector of Thornhill Church in Yorkshire and one of the 18th century's great forgotten scientists, Michell took Newton's view of gravity to its ultimate, dark conclusion. Michell's giant leap was to imagine a ray of light leaving a star in the same way we think today of a rocket leaving a planet. To escape the Earth's gravitational pull entirely and travel into space, a rocket needs to push itself upwards at 11 kilometers a second, faster than gravity tries to pull it back down. Michell knew nothing of rockets to the moon, but he did know that in theory, a massive star could have so much gravity that it would pull back into its clutches even rays of light traveling at 300,000 kilometers per second.
John Michell worked out that if you had a body weighing about 100 million times as much as the sun, light couldn't even escape from it. And he then went on to say that for that reason, maybe the most massive objects in the universe might be invisible to us.
Michell had explained how gravity could turn a star black, but not how it could turn it into a hole. A complete understanding of the life and death of stars awaited the nuclear age. Every star we see in the heavens has a giant nuclear reaction raging at its core. It's what makes a star like our own sun shine so hot and bright. Only the nuclear reaction holds gravity at bay. The energy pushing outwards, stopping the sun from being pulled tighter, smaller, and more dense. it's a precarious balance that gravity will always win in the end. When the sun runs out of nuclear fuel, its own gravity will crush it into a tiny ball the size of the Earth, but 100,000 times more dense. But our sun has too little mass and therefore too little gravity to become a black hole. Instead, astronomers call such a feeble ember a white dwarf. But when a giant star switches off, it goes with a bang. While we see the outward explosion as a supernova, this masks the implosion going on inside. The core has been given a gravity bear hug, so extreme that all the atoms have been squeezed into a ball of superdense subatomic particles called neutrons. It has become a neutron star, a mere 20 kilometers or so in diameter.
We know that ordinary stars like the Sun will become white dwarfs. We know that there are neutron stars, which are just a little bit heavier. And the question is, do you have beyond that? We believe it's black holes.
Theory suggests that when a neutron star is more than 3 times as heavy as our Sun, even the neutrons cannot resist gravity. The collapse is irrevocable. The density of mass becomes so great in the center that gravity overwhelms space itself, distorting it so horribly that it, and time with it, begins to wrench off from the outside universe. A darkness forms at the heart of the collapsing star and moves relentlessly outwards as the star's brilliance is sucked in. As the star dies, a black hole is born.
Skipper, a black hole. We've been pulled into a black hole.
Anna, compute its mass. Find out what you can about it.
Have we a chance?
I know so little about black holes, except that they're stars that have collapsed in on themselves. They not only bend light, they actually swallow it.
The forces inside a black sun are inconceivable. They're capable of anything. They can bend space, even time, turn both inside out.
Just how a black hole can manifest itself so powerfully in the emptiness of space is something that weighs heavily on Professor Stephen Hawking. Born exactly 300 years after Isaac Newton, Hawking now holds Newton's old job at Cambridge University. Hawking's mind roams free, not in Newton's universe, but in the universe of Albert Einstein.
We are used to thinking of gravity as a force that pulls bodies towards the Earth and pulls the Earth towards the Sun. But Einstein had a brilliant idea that gravity could be caused by space and time being curved rather than flat.
Einstein realized that nothing can exist at a point in space without existing at a particular time as well. Space and time seem to be woven together to form the flexible four-dimensional fabric of the universe, so-called space-time. Space-time is almost impossible to contemplate because our entire sensory existence is limited to the 3 dimensions of everyday experience.
Holy macaroni!
The easiest way for us to enter Einstein's universe is to imagine space and time to be like a sheet of rubber.
If space-time were empty, the sheet would be flat. But massive bodies like the Earth and Sun will bend the sheet and cause it to be curved.
This curvature is Einstein's concept of gravity. The more mass a star or planet has, the more steeply it bends space-time around it, and so the more gravity it has. Throw something extremely heavy like a collapsing star onto the sheet, and you soon end up with a universe full of holes.
Ow! Watch it, Coney! Oops.
As the massive star cools and shrinks, it will curve the spacetime around it more and more. Eventually, when it shrinks to a certain critical size, it will quite literally create a black hole in spacetime. Things can fall into a black hole, but nothing can get out.
Oh, there's so much I don't know about astrophysics. I wish I read that book by that wheelchair guy.
The most terrifying concept in astrophysics lurks at the bottom of a black hole: the singularity. Everything that has ever fallen into the hole is destroyed at the singularity, crushed into a pinpoint of infinite density and infinite smallness. Even space and time are squelched out of existence. All that remains in the outside universe is a perfect sphere of absolute darkness, a gravitational ghost of the star that died. This sphere is called the event horizon, and it marks the edge of the abyss.
This event horizon is not made of matter. It's, in some sense, almost not even made of a warpage of space-time. It's just a location. It is that unique location where gravity becomes so strong, just inside there, that nothing can escape.
While the event horizon may be only a few kilometers in diameter, the immense gravity of the singularity will have sucked a hole inside it that is impossibly deep to measure.
In the center, there is the so-called singularity, which is a place where, according to Einstein's theory, everything goes infinite, where if you do calculations, as it were, the smoke pours out of the computer and something goes wrong. And what that means is that deep inside black holes, we have a signal that we need some fundamentally new physics to understand what is going on.
Get it on the slit.
Astronomer Phil Charles thinks he has proof that such intangible objects are to be found in the real universe. The giveaway signal was the sudden burst of unexplained X-rays which alerted Phil to V404, a faint star trapped in orbit around an invisible compact object.
These are signatures of a star not much different from the sun, and it represents more than 80% of the light here. That we can follow and use the speeds that we measured to determine the mass of the object we cannot see. An excellent analogy is that of a big, strong man and a very small, light woman. As they swing each other around, the man hardly moves, and the woman, just by the balance of their weights, moves much more.
Calculations show that V404 orbits her heavy, mysterious partner once every 6.5 days. To achieve speeds like these, the partner must be very heavy indeed.
The mass that we measure by this process is 12 solar masses, 12 times the mass of the sun. That means it is substantially heavier than what we think is the largest mass of a neutron star. We are virtually certain it's a black hole.
The black hole has embraced V404 in a deadly dance, ripping gas from the hapless star and feeding it into a great disk of cannibalized matter. As this material spirals towards the hole, it heats up and sends a last desperate X-ray signal to the outside world. Nearly a dozen similar objects have now had their presence betrayed to astronomers in this same way by X-ray signals. One of the first was Cygnus X1.
I had a bet with Stephen Hawking as to whether Cygnus X1, a particular object from which one saw X-rays coming off, was a black hole.
Stephen Hawking bet that it wasn't.
That was not because I didn't believe in black holes. Rather, it was because I wanted an insurance policy. I had done a lot of work on black holes, and it would all have been wasted if it had turned out that black holes didn't exist. But at least I would have had the consolation of winning the bet.
When Hawking and Thorne made the bet in 1974, the evidence was thin. But as the years rolled on and the evidence mounted, Hawking felt it was safe to concede the wager.
And in 1990, Stephen Hawking happened to be visiting Los Angeles. He broke into my office and thumbprinted off on this bet.
I had given Kip Thorne a year's subscription to Penthouse, much to his wife's disgust.
This handwritten bet has come to symbolize the first real acknowledgement by the scientific establishment that black holes are really out there. Already, robot spacecraft have explored the planets. Someday, we may send an intelligent probe to a black hole in the depths of space beyond. Our mothership travels fast enough to insert into a safe orbit around the hole. A different fate awaits the probe.
As I approach the black hole, I will start to feel a gravitational tug on myself. It's a different kind of a gravitational tug or pull than you're accustomed to. Normally you think you're just pulled down. As I sit here in this chair, my head is farther away from the center of the Earth than my chest. And so my head is pulled less strongly than my chest is. So in fact, there's a difference in the pull. My head is being pulled less strongly than my chest, so I'm actually being slightly stretched apart by gravity. As you approach a black hole, that difference in pull becomes larger and larger.
As you get closer to the center, gravity will get more extreme, you will be squeezed and distorted. Spaghettification is the name some people use for this experience.
Spaghettification is an experience nothing can survive. The fragments streak down and into the blackness of the hole.
You or I falling into the black hole will get stretched and our bodies will get mutilated before we even reach the horizon.
It's no good. We can't break free.
Get him out, Alan. He's accelerating. We can't hold him.
Something else strange happens well before the event horizon is crossed. Not only space is being stretched, so is time. The closer the probe gets to the event horizon, the harder light from it struggles to escape. The mothership sees the probe slow down until it seems to stop. Time doesn't change for the probe because gravity is stretching its whole existence. But from the mothership's perspective, the probe has become frozen in time. It is both destroyed in an instant and hovering for eternity, depending on your point of view.
Nevertheless, if you are inside that spaceship looking back at me, you can wave, you can see me, you may think I can see you, but I can't, and you go inside the event horizon, you can still see out, you still see me on the outside, right up to the point that you die, you can still see me on the outside.
Oh my God, I'm gonna be sucked into a black hole, I'm gonna be sucked into oblivion, I'm gonna be nothing, and what's gonna be coming out the other side, I don't know.
I'll save you, Dad. I can't get any closer. You'll have to jump.
Piece of cake, son.
Crack, 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 Bart, what happened? Well, we hit a little snag when the universe sort of collapsed on itself.
We don't really know exactly what would happen deep inside a black hole if you were to fall directly in. It could be that something even stranger happens to space under these conditions, something like what happened at the beginning of the universe. And indeed, some people have speculated that in general it may be possible to avoid the complete singularity and emerge somewhere else.
Some say that if you pass through a rotating black hole, you end up in a new universe. A new dimension, even.
We've entered.
I recall a movie in which at the end of the film, the spaceship goes inside the black hole and comes out the other side into another universe. That don't happen. It just doesn't happen at all. The fundamental laws of physics say that at the center of the black hole there is a singularity, a region where space and time are infinitely warped, a region where when matter flows into it, matter gets destroyed.
But does this have to be so?
Ew, this is the worst place yet.
Speculation that tamed black holes may provide a way of cheating the laws of physics have become a hallmark of science fiction. Physicist Igor Novikov likes to speculate on what would happen if you join two black holes together to make a wormhole.
Wormholes are real bizarre objects. We can imagine a wormhole as two holes and some kind of a tunnel between them. But this tunnel is not in our space, and it is in some kind of hyperspace, outside of our dimensions.
This is really neat, Gene. This is a neat place for us to play, isn't it?
To make such a wormhole, we would have to engineer space-time. First, bend it until it begins to form a black hole, but not so much that a singularity is born. Then join the bottom of this gravity tunnel to the bottom of a second tunnel to make two holes connected by a continuous tube through hyperspace. Step 2 would be to move one hole to wherever it was you wanted to travel.
One of them can be near our Earth, another in another galaxy. But this tunnel can be extremely short, say a few meters.
The tunnel would also be very fragile, prone to collapse as soon as a traveler attempted to pass through it. But if we could develop the technology to tame the ferocious forces at work, we would have opened an interstellar shortcut.
He can travel from one galaxy to another galaxy only during, well, let's say a few seconds.
Where a black hole is a one-way street with a dead end at the singularity, a wormhole will be a freeway to the stars.
I have to say, these things are driven by sort of romantic science fiction ideas, which is fine. I mean, a lot of science is driven that way, and you do good things. I have nothing against that directly. It's just that it seems to me that the scientific evidence is just that this is not going to happen. It's just not possible.
Oxford University's Roger Penrose pushes the mathematics of black holes in a different direction. He's formulated a way to extract enormous quantities of energy from the way black holes spin, at the same time as sending enormous quantities of garbage to oblivion. In the real universe, most black holes should spin because the stars that formed them would have been spinning as they collapsed, their massive gravity swirling the fabric of space around them like water around a whirlpool. Penrose's energy extraction process would require building a power station at a safe distance around the spinning hole.
You could imagine firing a lot of particles or bodies into the neighborhood of the spinning hole in the right direction.
The forces of spaghettification will rip these particles apart.
One particle carries negative energy into the hole, and that means that the partner has more energy than the one that fell into it. So you can actually extract energy from a black hole through this process.
The particles could be any old rubbish you never wanted to see again. Half would disappear into the hole, half would be flung outwards with a slingshot of gravitational energy that could be used to drive a turbine.
The source of that energy is, in effect, the slowing down of the black hole's rotation, because as these particles keep falling into the hole, they gradually slow it down. But since there's usually an enormous amount of rotational energy in a rotating black hole, this would be an extraordinarily efficient way of extracting energy.
But there is a long way to go before observational science catches up with the wilder speculations of black hole theory. Another country, another telescope. The hunt takes Phil Charles to Australia.
Australia has access to the southern hemisphere of the sky, and there we can see the Magellanic Clouds. And the Large Magellanic Cloud is our nearest neighboring galaxy. And there are about half a dozen very interesting compact objects that we want to study from here. We need to get maybe 20 or 30 so that you can really see the population of black holes that we're looking at. Do they all have similar masses? Are they a spread of mass? Do they all come from the same kinds of original stars? We can start to work that out once we can get enough of them.
While Phil Charles turns his sights on the stars of our neighboring galaxy, other astronomers are probing galaxies further afield. Here they are finding objects of staggering immensity, formed not from the death of a single star, but from the collapse of enough matter to make millions. Such objects, astronomers now believe, are supermassive black holes. Ever since radio telescopes began eavesdropping on the heavens, the strongest and most puzzling signals have come from the hearts of distant galaxies. Astronomers now suspect these radio signals are generated by central supermassive black holes. Mighty jets of energized particles are blasted into space from an invisible engine that drives these so-called radio galaxies like great wheels through the heavens. Nameless stars are ripped apart by an immense gravity to feed central disks of white-hot matter, shining 100 times more brightly than a whole galaxy of stars like our Milky Way. Powering everything is the hidden central object, as small as our solar system, but where enough matter to make millions or even billions of stars has undergone a titanic gravitational collapse.
Look at the numbers. Tonight we're looking at the radio galaxy M87. M87 is a nearby giant galaxy which is very unusual in having a large, powerful jet coming out of it.
M87's jet is like an enormous death ray of charged particles moving close to the speed of light and 6,000 light-years in length. The jet is a signature of the way the black hole is swirling matter and space around it. Astronomers use the speed of this swirling matter to calculate the black hole's mass.
Well, we're talking about a black hole which is 1 billion solar masses or more, which is therefore is much larger than anything we are used to seeing in our own galaxy. But is fairly typical of what we think many radio galaxies have in their nucleus.
Astronomers suspect radio galaxies are those galaxies with plenty of matter left for the black hole to eat. If a galaxy appears quiet, it's probably because the black hole has run out of food.
If we look in the center of almost any galaxy, there should be lurking a dark mass of millions of solar masses at least, which may be the remnant of some past activity in that galaxy. And in the last few years, there's been growing evidence that these dark masses actually do exist.
But seeing them is still beyond us. Even the latest high-resolution Hubble images can show only the bright central disk, the jets of energized particles, but not the black speck in the middle. We will never be able to appreciate the full majesty of a supermassive black hole from Earth. Time for our spacecraft to make another journey.
If one was to take a journey starting in the outer part of a galaxy and moving in, you see very hot glowing gas filling the galaxy, which is being heated by some mysterious, powerful central source. You would find gas orbiting in a disk, swirling at nearly the speed of light and getting very hot. Getting so hot that it radiates not just visible light, but very energetic radiation like X-rays.
It is one of the great cosmological contradictions that the larger the black hole, the weaker the gravitational forces near the event horizon. This time, there is no spaghetti. As we approach the event horizon, the intense gravitational curvature wrenches the light from the universe to a bright point directly overhead. We have reached the point of no return. We are now inside the black hole. But where is the singularity?
If you were falling into a black hole and the singularity, you knew from your calculations that the singularity was out there and you're heading for it, you look at it, you don't see it. It's like a singularity that you're heading for in the future, and you don't actually see it.
The singularity is where science ends and speculation begins. Space and time have ceased to exist, replaced by a seething chaotic mass we can call quantum foam. Into this bizarre conjecture has disappeared all the mass and energy that has ever fallen inside the event horizon. This is where Einstein's laws fail. This is where the laws of quantum mechanics fail. This is where the secrets of the universe are hidden.
The singularity is an object at the core of a black hole that is governed not by the ordinary laws of physics that we're familiar with, but by the laws of quantum gravity, which we only are beginning to glimpse and understand.
If the probe was strong enough, it would fall towards the singularity for perhaps an hour, until it blindly met its future at the end of space and time.
You would then experience the final crunch in the center, learning in your final moments the new physics prevailing at those times perhaps, but you'd be able to send no signal to the external world of the interior region.
What really happens to it at the end is as unknown as what happened before the Big Bang. It's the other end of that story.
We do expect to find singularities in the Big Bang. Well, of course, that was the first one we had to worry about. Black holes, and in the Big Crunch, if there is one.
Is about the virial temperature. The electrons may be rather cool.
What we have, of course, is two tornadoes orbiting inside a larger tornado and coming together and colliding and coalescing.
The world's leading cosmological minds can now gather to talk with facts and figures about what was not long ago dismissed as flights of fancy.
What we're showing, of course, is that observationally it can't be a neutron star.
It seems our understanding of the nature of the universe is accelerating almost day by day.
These are the facts. It seems that most nearby galaxies, and perhaps therefore most galaxies, harbour a central black hole. Our galaxy would seem rather underprivileged if it didn't have one as well. The evidence has come only in the last few months that makes this a compelling case.
Astronomers are virtually certain that hidden behind the dust in the center of our own Milky Way galaxy, there is a black hole weighing 3 million times the mass of the Sun.
Our first object. You think even as little as 5 years ago, people thought that we could get away with not having to have black holes in our own galaxy. We could explain almost everything that we see by neutron stars. No theorist now believes that we're dealing with ordinary neutron stars anymore. There are things out there that they have to be compact and they have to be explained. And I think that's an extremely exciting prospect.
Everybody has trouble coming to terms with black holes. Locked within these prisons of light are the secrets of the universe. Where did it come from, and where is it going to? We may never answer these questions, but for once, we know where the answers are hidden.